Hello crew, today we're going to talk about the exchange of energy between gravitational potential energy and kinetic energy. To start that conversation, we're going to look at different ways that energy can be stored, but we're going to have a real focus on gravitational potential energy and kinetic energy. Towards the end of the video, I'm going to talk about how these two things are exchanged between one another. But we will have to deal with the reality that it's not a perfect exchange and that heat is lost. Frictional powers tend to cause us to lose some energy in the exchange. So to start, here is energy, and you know there are a wide variety of ways to store energy. The sun uses a nuclear process, meaning it stores its energy in some of the forces that hold the nucleus of an atom together. Things like rubber bands can store what we call elastic potential energy. These are attractive forces within the molecules that cause them to want to move closer to each other. Energy can be stored in chemical bonds like that of the wax of a candle, or in something as simple as a potato, where our bodies can recover that energy. The energy of motion is kinetic energy, and that's one that we'll talk about a lot today. We also have gravitational potential energy, which is the energy that's stored in an object that is moved far away from a very massive object like the Earth. And for this to make sense, let's go ahead and take a look at it in a little bit more depth. In my example, I will use a rock. You know that this rock is in equilibrium. There's a weight acting downward, and then the normal force from the surface of the Earth is pushing up on it so that it's in equilibrium. I could put myself into this picture and I could say that I lift the rock. Now I am applying a force to the rock in the upward direction that's countering the weight of the rock. I had to do some work on this rock, lifting it a height h in order to get it into the air. It may not initially make sense that this rock now has more energy associated with it, but certainly I could ask it to do a job for me. I could put this rock in a simple machine, ask it to do some work in turn. Because of this downward force, the force could be harnessed to do some sort of job. And by definition, it means that that rock did some work for me as a physicist would define work. Let's go back to this picture for a moment and figure out how we can quantify how much potential energy this rock has. We're going to hone in on these particular variables, and we're going to put up this equation. Potential energy is equal to mass times the gravitational acceleration times h, where it's the height relative to some reference location. If we take a brief look at the units, we will see that we have kilograms from the mass, meters per second squared from gravity, another meter from the height that the rock has been elevated. Combining this, we get kilogram meters squared per second squared. There's a derived unit in the metric system called the joule that represents these base units. We will also use it. It is the symbol capital J. Let's leave this alone for a moment and move to kinetic energy. Kinetic energy is the energy of motion. For example, I could say that I have a baseball that's traveling through the air with some velocity. We can mathematically define the kinetic energy as 1/2 mass times velocity squared. Notice that the kinetic energy is actually proportional to v squared, meaning that if you were to double the velocity of an object, you would quadruple the kinetic energy. Similarly, if you were to triple the velocity, the kinetic energy would increase by a factor of 9. If we look at the units for kinetic energy, we can find that we still have kilograms from the mass, then we get meters per second from velocity, of course that is squared, which leads us to kilograms meters squared per second squared again, which was a joule. Of course, anytime that you have like units, you can add terms together. Frequently, people like to add kinetic energy and potential energy together into something that they call mechanical energy, which of course would still have units of joules. The benefit is that if we look at mechanical energy for an object that is in free fall, we can say that the mechanical energy is actually constant for the entire trip. It doesn't matter if the object is traveling up because it was thrown into the air, or if it's falling down from rest. At any point in time, we can say that the potential energy plus the kinetic energy is constant. I'm going to show this example with a ball that starts from rest and is dropped into the air. So when it starts, all of the energy is tied up into potential energy. But once the ball is dropped, it starts to pick up some speed, and you can see that the kinetic energy starts to actually increase while the potential energy is going down. This trend will continue, but notice that the mechanical energy is staying constant until we actually reach a point where at the end, just before the ball hits the ground, we could say that the energy is entirely tied up in kinetic energy. So the ball is moving as fast as it's going to be moving. But because you've now reached the reference location as far as the height is concerned, there's no potential energy anymore. Notice that when you look at this graph, I'm actually plotting the distance fallen on the horizontal axis as opposed to the time. Recognize that certainly the ball is picking up speed as it falls. So the time interval in between each of these points that I'm showing here is actually decreasing as you move to the right. So if we look at this situation a little bit closer, we have that the mechanical energy PE plus KE is equal to the mechanical energy PE plus KE because mechanical energy is conserved for an object in freefall. I'll put some subscripts on this and say that on the left hand side I'm looking at what the ball was doing when it was at the top of its path, and on the right hand side we'll say we're looking at the ball at the bottom of its path. I'm going to expand out each of these terms so that we can see all the individual components that make them up. And we'll notice something interesting. For the situation that I have a ball starting from rest, I can completely get rid of the kinetic energy term on the left hand side. That's when the ball's at the top because it has no velocity. And on the right hand side, I can say that we have no potential energy whatsoever when the object is located at the reference point because the height is equal to 0 and that term goes away. That simplifies the equation down quite a bit for us. The next step is to notice that mass appears on both sides of the equation, so we can divide it out and it goes away. That leaves us with something that looks like this. Now we can do a little bit of algebra. I'm just going to rearrange some terms, push the 2 to the other side, square root both sides, and we get an equation that looks like this. This equation can easily tell us the velocity of an object, assuming that it is dropped from rest and that there are no frictional forces. Let's take a look at how that works. I'll start with this example where we have a baseball that's falling towards Earth. I'll define the height as 2 meters. The reference location is the surface of the Earth. The question is, what is the velocity right before the ball strikes the ground? We're not interested in what happens after the ball strikes the ground. That includes an impact, and we're not trying to complicate this particular system in that way. I can say that the ball fell 2 meters and totally converted all of its potential energy over to kinetic energy. So I plug in my 2 meters into the height underneath the radical, and you can see that I can simply calculate that the velocity of the ball would be 6.26 meters per second just before it strikes the ground. What if you wanted to know how fast the ball was traveling, say 1.5 meters below its starting position, or that is to say half a meter above the ground? All you have to do is conceptually change the reference location. For this particular problem, we will now say the reference location is located 0.5 meters above the ground. That's where all of the potential energy would go away. You can see here that the initial height of the ball would just be 1.5 meters away from the reference point. Again, I can say that all of the potential energy in this situation would be converted over to kinetic energy with no potential left over because now I've changed my reference location. And I could solve this out and find that the velocity of the ball is 5.42 meters per second. The true beauty of this equation is that it doesn't have to be limited to vertical situations. Let's say in this situation we want to know how fast the ball is going to travel over that little hump in the road, and for convenience I'm going to go ahead and say it also is located at 0.5 meters. So we will say that our reference location is still located at 0.5 meters above the Earth. The ball is ultimately still converting all of its potential energy over to kinetic energy. So in this situation, we still find that the ball would be traveling at 5.42 meters per second. When using this equation, it's really important to recognize that there are certain constraints about it. The first requirement is that the object must start from rest. Remember that this equation assumes that the kinetic energy is 0 at the top. The second requirement is that V bottom is only valid at the reference height. Although keep in mind that you can adjust the reference height as needed so that you can look at different parts in the path. There's also a big assumption in this guy that there are no energy losses due to friction. If you have a situation where you can't make these assumptions, we do have a method that we can look at. We go back to this original equation here, and we just need to add another term. In this case, we're going to add a lost energy term onto the right-hand side. You can start with a certain amount of mechanical energy and then have an event where perhaps you throw a ball into the air or something is falling. After the event, you may calculate that you have less energy than what you started with. It's fairly easy to say that that energy went to friction, and that's the lost energy term that I'm highlighting here. Let's go ahead and expand this out to show all the terms again. A common problem may give you the following information. You may still have the initial and final heights, the mass of the object, the initial and final velocities, and from there you'd be able to calculate how much energy is lost. Here's an example situation. Let's say that I have my daughter in a swing and I pull her back so that the swing is now 1 meter above the reference location. We'll call the reference location the lowest possible point in the swing. I could use our simplified equation and say that I would predict that my daughter in the swing should have a velocity of 4.43 meters per second as she goes through that lowest point. If I take a measurement and find out that she only has 4.0 meters per second of velocity, I can identify that we had some losses of energy somewhere in the system. Let's go back to this equation and notice that we can still say that since the swing started from rest at the top, that I can get rid of that kinetic energy term on the left. I still have a swing that is going through the reference location, so I have no potential energy on the right. Again, this simplifies my equation down, and I can plug in my numbers. Notice that on the left I have my original height of 1 meter, but on the right I have the measured value for velocity. When I crunch these numbers, I can find that I have 196 joules of energy to start with, but I only have 160 that I can identify in the kinetic energy towards the end. The lost energy is 36 joules, which is from my frictional losses, perhaps due to air resistance or friction at the pivot point of the swing. Let's recap some of what we've talked about. We have this term mechanical energy, which is equal to the kinetic energy plus potential energy, and I'm showing you how we can arrive at the kinetic and potential mathematically. Remember that the mechanical energy is actually conserved for an object that's in free fall. Again, my examples tended to show objects that started with potential energy and went down to gain kinetic energy, but remember you could always do this in a reverse and say that you have a certain amount of kinetic energy starting, launching something into the air, figure out how much potential energy it's going to have in the end. For a simplified situation, we can say that the velocity at the reference point is equal to square root of 2gh. Just remember that the requirements are the object must start from rest and the velocity is relevant at the reference location. This equation also cannot take into account any frictional losses. If you need something that is a little bit more complex and you cannot make all of these assumptions, you can certainly go back and use the full set of terms that we used when we were looking at the swing example. That's all I have for you right now, so as usual, if you think you've got everything figured out, let your computer know.